Hello, welcome to another module in this massive open online course. In this module, we will start looking at a digital communication receiver, that is what are the different schemes or what is the kind of signal processing the processing that can be employed, the optimal processing that can be employed to get the best performance at the receiver in a digital communication system. Alright. So, let us start looking at the operation and implementation of a digital communication receiver. Okay. So, we are going to look at a digital communication receiver, that is basically the receiver in a digital communication system. We already looked at the transmitter, that is the pulse shaping operation, what is the transmit spectrum, the power spectral density of the transmitted signal. Let us now look at a digital communication receiver. Okay. So, when we talk about a digital communication receiver, the schematic of a typical digital communication receiver can be as follows. Alright. So, let us look at a typical schematic diagram of the digital communication receiver. I have the transmitted signal xt, okay, transmitted signal xt, the noise, additive noise, as we have seen in the previous module. So, that gives the received signal yt. This is our simple additive noise channel model, and if the noise is white Gaussian, then this is our additive white Gaussian channel. This signal yt is subsequently passed through a filter. This is an important concept, through a filter, which is basically an LTI system. LTI stands for linear time invariant system, followed by sampling at the symbol time instant, and that sample is denoted by. So, this is basically your sampling operation, and this is sampled at the symbol time capital T. At T, where T equal to symbol duration. And this is a schematic diagram. Of a digital communication schematic diagram of a digital communication receiver. Okay. So, we have the signal xt, to which there is additive noise nt is added, we get the received signal yt. This signal yt is passed at the receiver, is passed through a filter, alright, which basically is a nothing but a linear time invariant system. It is passed through a filter ht, alright. You can also call this as a receive filter, followed by sampling it, alright. It is sampled at capital T, where T is the symbol duration, alright, and the transmitted digital communication symbol, the information regarding the transmitted digital communication symbol is extracted from this sample R of T, alright. So, we can say this is followed by detection, okay. For instance, this is followed by, you can say, detection, okay. And what we have to see is what are the schemes, okay. This is followed by detection. So, detection in the sense that we have to extract information regarding the transmitted symbol. So, there are several components to this. One is of course the filter, right. And then after you sample, how is the information regarding the symbol extracted from the sample. So, all these things remain to be seen, and we will look at these concepts one by one, alright. So, what is the filter? First we will start by addressing the question, how can the filter HT be designed, that is received filter in a digital communication system, how can that be designed, okay. So, let us take a look at that. So, I have, if you look at, if I call this, so this I call this as a filter or basically receive filter, if I call this signal as R of t, okay, that is output when Yt is passed through Ht, that is R of t, I can say R of t, R of small t, that is a continuous time signal, is Yt pass through Ht. When you pass a signal through a linear time invariant system, correct, the output is a convolution of the signal with the impulse response. So, Ht is basically nothing but the impulse response of the LTI system or the impulse response of the receive filter, okay. So, this is impulse response of LTI system or basically the receive filter. Or you can also term this as the receive filter, okay. And now therefore, I can write this, remember the convolution can be expressed as the integral minus infinity to infinity y t minus tau h of tau, this is the convolution operation, okay, continuous time convolution or in fact linear convolution, okay. And now we know, let us assume we know the transmitted, we know, well, what do we know? We know Yt equals xt plus n of t. So, this is our additive noise model, okay, or you can say this is our additive noise channel. And further we can assume that this xt equals a naught, let us make the model simple to begin with, a naught times p of t, where a naught is the symbol, p of t is the pulse, we have seen this before. So, okay. So, a naught is the symbol, p of t is the pulse. So, this is our model for x of t. So, this is our model only for x of t. So, let us say this is equal to x of t. We have seen this model before, the transmitted signal x of t is nothing but a naught pt plus a1 pt minus tau, the pulse shifted by t, capital T, where t is the symbol duration and so on, and the sum of all these modulated and shifted pulses. However, to keep things simple, here we are assuming a single pulse, that is a single symbol a naught and a pulse, okay, and this can be readily extended to the more general scenario. However, let me just be clear, to make things simple, to make the following derivations and the following analysis simple, I am restricting it to a single symbol a naught, alright, and pulse pt, okay. And so therefore, what I have here is I get this is equal to a naught pt plus nt, again let me mention here, this is for simplicity, okay, just to make the initial presentation and the ensuing analysis simple, okay. Now, a naught is the symbol, pt is the pulse, okay, and now therefore, if I substitute this in the expression for RT, now what I am going to do is I am going to take this Yt, expression for Yt, and I am going to substitute this in the expression substitute this in the expression for RT, and what I am going to get is that RT equals integral minus infinity to infinity. Well, we already know it is yt minus tau into h of tau, but yt is a naught pt, yt minus tau is a naught pt minus tau plus nt minus tau times, or let me write it down, times h of tau d tau. Okay. This is RT. Now, let us consider the sample of RT. Now, this, remember, this RT is sampled at t. So, let us consider the sample at capital T. So, sample at t, which means I have to substitute small t equal to capital T, that is nothing but minus infinity to infinity a naught p of capital T minus tau plus n of capital T minus tau times h of tau d tau. Okay. This is the output signal RT, output of the linear time invariant system RT, sampled at capital T, where capital T is the symbol duration. Okay. Now, let us separate this into signal and noise components. Okay. So, now I can separate this into signal and noise components, that is, this is nothing but integral minus infinity to infinity. Of course, a naught is constant, a naught is a constant symbol. Okay. So, this will be come outside of the integral, it does not depend on the variable of integration d tau. So, this is a naught p t minus tau h tau d tau plus integral n capital T minus tau h tau d tau. And now, you can see we have separated this into the signal and noise components. This is your signal component. Okay. So, this is the signal component. And this is your noise component. Signal component. So, we have the signal component, we have the noise component. Now, the point is, the question that we would like to address, as I have already described, how does one choose, how to choose the filter h tau. Okay. How to design, or rather how to, rather than choose, I have to say how to design, how does one design this filter h of tau, that is, how does one optimally design this filter h of tau. Now, we have the signal power and we have the noise power. Now, realize that we would like to maximize the signal power while minimizing the noise power. So, the noise is the undesired signal, we would like to minimize, right, we would like to minimize the noise power while maximizing the signal power, or in other words, we would like to maximize the signal to noise power ratio. That is, if we have a ratio with the signal power in the numerator, noise power in the denominator, we would like to maximize the signal power, minimize the noise power. Therefore, we would like to maximize the signal to noise power ratio. That is something that is very convenient to consider in a communication system. So, the most typical metric that you will see to characterize the performance of a digital communication receiver is the signal to noise power ratio at the output after processing the received signal. Okay. So, that is something that is fundamental, which you might have already seen before. So, the objective is, so we have dual objectives really. So, I could call objective. So, objective is maximize signal power to minimize the noise power. So, we would like to maximize, and both these things together you would like to maximize signal to noise power ratio. This is defined as SNR. So, this is a fundamental quantity in the analysis of a communication system. So, we have the SNR, which is the signal to noise power ratio, which is equal to your signal power divided by noise power. This is the signal to noise power ratio. Okay, and this is a fundamental quantity in the analysis of a communication system. For analysis of performance not only a digital communication system, for that matter any communication system, actually even analog communication system, because noise is an inevitable part or inevitable component in any communication system. So, the signal to noise power ratio is one of the central metrics which is used to analyze the performance of a communication system, any communication system, in particular in this context the performance of that of a digital communication system. Okay. So, now let us see what is the signal to noise power ratio for this digital communication system. Okay. So, we have the signal power. Now, let us look at the signal SNR signal. This is A naught integral minus infinity to infinity, well P t minus tau h tau, this is your signal. So, signal power would be a slightly bigger term. So, let me write this completely. Expected value of A naught minus infinity to infinity P t minus tau whole square. This is equal to expected value of, well, I can separate this as expected value of magnitude A naught square into expected value of magnitude of minus infinity to infinity P t minus tau h of tau d tau whole square. Considering only real signals, I can even drop the magnitude, but this is fine, it is general. So, or let me just drop it, considering, let us say consider only real signals. Okay. I can simply write this as expected value of magnitude A naught square minus infinity to infinity P t minus tau h of tau d tau whole square. Okay. So, this is your signal power. Now, if you look at this, now there are two interesting things in this. First, we know that the symbols, symbols are random. Okay. These are the information bearing symbols. So, these are random. Okay. And we have characterized the power of the transmitted symbols. We have used the notation to represent the power if you remember correctly, the power of the transmitted data symbols, we have termed that as PD. So, expected AI square we have denoted by not A naught square, but expected AI square I have denoted it by PD equals the power of your data symbol. So, the power of the data symbols is expected. So, PD, we have PD is expected magnitude A naught square, that is the power of the data symbols. Further, if you can look at this quantity over here, you will realize something important. It depends only on the pulse P and the receive filter HT, both of them are not random, that is the pulse PT is fixed, alright. Once you design the filter H, the impulse response HT is also fixed. So, both these quantities are deterministic, there is nothing random about these quantities. So, this expected value is simply equal to the quantity itself. So, let us note that also, since PT and HT are fixed, these are deterministic quantity, or in other words there is nothing random about them. Therefore, this quantity, the signal power will simply be PD. Now, put these things two things together, this will simply be PD minus infinity to infinity. We have, I think, PT minus tau H tau d tau whole square, where we have got the rid of the expectation because this is a deterministic quantity. So, this is basically your signal power, okay, and that is the first important thing that we can realize. So, this is the signal power, okay. So, we have computed the numerator term in the signal to noise power ratio, alright. So, with this let us stop this module here. In the next module we are going to look at how to evaluate the noise power, compute the signal to noise power ratio, and then derive the optimal, from that derive the filter which maximizes the signal to noise power ratio, okay. So, we will stop here and continue in the subsequent module. Thank you very much.